We continue description of piezoelectric effect using thermodynamics. And last time we have shown how by using Maxwell relations we can show that direct and converse piezoelectric effects are thermodynamically equivalent. We will extend this now to dielectric and elastic tensor and derive and look at additional constraints that thermodynamics imposes on symmetry of piezoelectric effect. Before we start, I would just like to mention something that I probably should have done before, but I somehow assume that everyone has to be familiar with that. But nevertheless, let me say, when I'm writing, for example, relation like this, every time I have repeated indices on the same time of the equation, that actually means that I'm having a summation over those repeated indices. This is so-called Einstein notation, which I assume in all equations that will be written just to avoid writing this summation sign. And in general, if I'm writing the I, for example, and AJ, that simply means that for an arbitrary direction of electric field vector, the electric displacement vector can be in some also some other arbitrary direction that they don't have to be aligned, and that simply reflects anisotropy of the material. Okay, so let's look at dielectric permittivity tensor. First, dielectric displacement is given by this relationship here, derivative of free energy with respect to EI, and then the second derivative or first derivative of the electric displacement actually defines the electric permittivity. We can write it like this by using this formula here, putting it over there, and then just as we said before, the order in which we do this second derivative is not important. I get that derivative of dI with respect to EJ must be same as dJ with respect to EI, and that means that these components of the dielectric tensor, the electric permittivity tensor, must be symmetrical with respect to the diagonal of the tensor. So instead of having 9 components, we will actually have only 6 independent components, and this tensor of the second rank and all other tensors of the second rank will be symmetrical with this. And this is not considering at all symmetry of the crystal. This just comes for all materials from thermodynamics. So let's now look at elastic relations. First of all, let us look at the definition of a stress tensor. This is something that you have done in mechanical and other courses, and I really don't want to dwell too much on it. But basically, you have components of the stress tensor with along the axis 1, 1, 2, 2, 3, 3, which means that force is acting on the surface which is perpendicular to the direction along which the force is acting. And then we have a shear components which again, the first index describes the direction on which the force is acting, and the second index is describing the surface on which that force is acting. And the surface is defined by the axis which is normal to it. Now we have for intrinsic symmetry of the stress tensor that sigma KL must be equal to sigma LK. And if you need some more details, please check Nice book for this. He has a nice discussion about that, considering cases when you may or may not have torques and so on. So basically what this means that, for example, sigma 2, 3 is equal to sigma 3, 2. We start with that fact. Now we can use Maxwell relations for compliance and stiffness tensors, basically Young modulus. But first we apply what we just learned, and that is that sigma KL, it must be equal to sigma LK. That immediately gives us for this tensor of compliance, which is a tensor of the 4 rank, which has 81 components, gives us only 36 independent components because of this symmetry. And then we apply Maxwell relations. Here we start with the definition of Sijkl as a derivative of strain versus with respect to the stress. We put definition of the strain, which we showed on the previous slide here. We invert order in which we do derivatives, and we get that SKLIJ must be equal to Sijkl. So we have only 21 independent components of the elastic tensor. And that's like that for all materials before we apply any symmetry of the crystal which comes on the top of that. So let's see what we can say about piezoelectric tensor. It's a tensor of the 3rd rank. And let us look at how we can determine these individual components experimentally. So we apply pressure and we measure charge, and we can determine the piezoelectric coefficient. So let's first take the situation in which we apply only diagonal components of the tensor, sigma 1, 1, sigma 2, 2, sigma 3, 3, and assume that all others, the shear components, are equal to 0. We then get the following components. For example, we get that D1 can be equal to D1, 1, 1, sigma 1, 1, or D1, 2, 2, sigma 2, 2, and so on. And for each of those cases, we have only one pressure and one charge, and therefore it is possible to experimentally determine all these coefficients. However, if we now take the cases in which the shear components, where we know that this applies, are different from 0, and the other components are equal to 0, we get this. These two are equal, and we get that we have two different piezoelectric coefficients. For example, if we take sigma 1, 2, which is equal to sigma 2, 1, different from 0, and all others equal to 0, we get that D1 is the sum and equal to this. So we have one pressure and one charge, and we have two piezoelectric coefficients. It is not possible to get these piezoelectric coefficients separated. They cannot be resolved experimentally. So what we do, we take that they are equal, and that will facilitate consideration. So out of 27 components of the 3 times 3 times 3 components of the piezoelectric sensor, we have 9 that are related to other 9, and that means that we have 18 independent piezoelectric coefficients. That's the maximum, and this can be further reduced by taking into account crystal symmetry. And that's something that we will do later on. Now, since piezoelectric coefficient is a tensor of the third rank, this is inconvenient to express on a paper, on a screen, which is two-dimensional. So we would like to flatten this tensor of the third rank, this three-dimensional representation, into two-dimensional, and we use the following notation, which was developed by Voigt for mechanical and then extended for piezoelectric relations. So here is what we do. We write Dij k as dim, where I we write as I, and when j and k are equal, we write m as j, and when j and k are different, those are these cases, we write m as either 4, 5, or 6. So for example, D1, 2, 2, we write as D1, 2. So that's this case here. And D1, 3, 2, we write as 1/2 D1, 5, which is this case 2. This factor of 2 comes from what we just said before. So this is written here, summarized here. So how do we write this matrix? Well, here it is. It's 3 times 6 matrix, which does not behave as a tensor any longer. If you want to make its transformation from one coordinate system to another, you don't use tensorial transformations, which we will discuss later. You can still transform it from one coordinate system to another, but relations are different. And if you are interested in this, you can look in the book by Newnham. I will not spend time on that. Since we have flattened tensor of piezoelectric coefficients, we also have to write stress tensor differently. So we start with a second rank tensor written like this. We use these abbreviations. These are the same as we used for a piezoelectric effect. And then we write it as a vector of the first rank. So we go from the second rank tensor into the first rank tensor. Again, this doesn't transform as a tensor. So the direct piezoelectric effect in a matrix form would be written in this way, where we have a 3 times 1 vector, then we have a 3 times 6 matrix, and then 6 times 1 matrix. We can explicitly write it, this sum. Remember, Einstein convention, repeated indices, it's actually a sum, and we write it like this. For example, for this first component D1, we multiply this by that. We write it like that, and then we can develop it into the full format. and that's written here. You see these two terms and these two terms is where we assume that 132 and 123 are equal. We can do the same with in a tensorial form, and we again for D1 get the same equation as before. So you can compare this with this. Now, for a converse effect, we have electric field, we have a piezoelectric tensor. Note that the first index in a piezoelectric tensor always corresponds to the electrical variable, and the other two correspond to mechanical variables. I think I haven't mentioned that, but the piezoelectric tensor for a direct effect is just transposed tensor of the converse effect. And you can see that by comparing equations for direct and converse effects, but that's less important for us. Now we have also symmetry of the strain tensor. Epsilon jk must be equal to epsilon kj, and that immediately means that dijk must be equal to dikj, which we also got in a direct effect, and it indeed has to be so. And now we write strain equation in this format. There is this factor of 2 which comes from these other definitions that we have used, which is related to these other definitions that we have used so far. So that we write piezoelectric converse effect in this format, collapsing it into two matrices, and in a matrix format, the strain tensor, the converse piezoelectric effect, strain tensor piezoelectric, strain vector piezoelectric matrix, and electric vector, electric field vector would look like this. Again, these are vectors and matrices. They don't transform as tensors if you write this equation in its full form. And this is 6 times 1, 6 times 3, and 3 times 1 expressions. Okay, so here is this statement that matrix, that tensor of the converse effect is tensor of the direct effect just transposed. If you compare this, and for a direct effect, you will immediately see that. So the summary of this notation also extended to elastic effects, and this is, as I said, Voigt. Voigt, I think that's how it's spelled, is written here. For D, we already did, and here you have rules of writing elastic compliance or elastic stiffness tensors. Okay, so these coefficients can be written in this format, in a matrix form. Remember, these are not tensor, these are now matrices. K is still tensor. This is polarization vector, or pyroelectric coefficient vector, sorry, it's polarization dependence of polarization with the temperature. So pyroelectric tensor is dependence of polarization with respect to temperature, permittivity, piezoelectric, and elastic compliance. You will find in the books that they are presented in matrices like this, which are symmetrical with respect to the diagonal. Here you have elastic compliance or stiffness. Here are piezoelectric coefficients. You see that these are transposed. This is the electric permittivity. This is pyroelectric coefficient. This is piezocaloric or thermal expansion coefficients, and this is heat capacity, which is the scalar. This is the most general one for a triclinic symmetry, and as you go to other symmetries, we lose some elements. They become zero because of the symmetry of the crystal, but that is something that we will discuss later. I just want to show you this if you find it somewhere in the literature to understand what it is. So this is S matrix, this is piezoelectric coefficient matrix transposed. This is thermal expansion and piezocaloric effect. This is dielectric permittivity, and this, I think, heat capacity. So this is for isotropic material, and this is for some other classes. And as I say, we will look at this in some details later on. First, why in some material piezoelectric coefficient is absent, all elements are zero, and why in some of them, many of them are zero, some of them are equal, and so on. Okay, so I will stop here with this part, and next time we will continue with other sets of thermodynamic variables. Right now we are using temperature, electric field, and stress, but those are not the only experimental conditions with which we can work, and we will see how these relations change and what does it physically mean if we take another set of variables.